Okay, everyone. June 2022, paper 5, variant 1. This is the first paper that we want to do today. You should let me know the questions that you want me to discuss from this paper. We will start from them. So right now, I see 3 questions that you guys have voted for. What I'll do is I'll quickly go through the paper myself as well, in which there's another question that also looks kind of tricky. So you can have a look at that as well. Okay, so yeah, June 2022, paper 5, variant 1. We want to do difficult questions from this particular paper. Okay, so the first question is about permutations. You have to arrange these 8 letters, these together, 2 D's together. That's pretty straightforward. The 3 E's are not all together. Not all together means you have to find the case where all of them are together. Subtract that number from the total. All right, that's what you would do. Okay, so you can do that. The first part looks relatively straightforward. Then the first question looks relatively straightforward. The second one is about combinations. So you've got 8 men, 6 men, 8 women, and a committee consists of 5 of its members. And these 2 people have to be on the committee. Then it says, then this Mrs. Land must be on the committee, and there must be more women than men in the committee. Are you sure you guys can all do this? No problems in this? No problems in this? Okay, so I would suggest to everyone focus on what is in your control now. Just focus on what is in your control. Forget about what happened today. Now, of course, it's difficult, but now you've got 3 more papers to go for maths, right? You've got M1, you've got S1, you have paper 3, those of you are doing composite, and then those of you are doing AS, you still have 1 more paper to go. So it's better to focus on that, focus your energy on that, try to prepare as well as you can for the remaining papers. What happened today has happened. We will figure out, we will actually hear what is going to happen about this paper, whether it's going to be predicted grades or whether it's going to be a retake or whether they're not going to do anything about it. That's not in our control, right? So that has happened, whatever has to happen, whatever had to happen today. So you can just, focus on what is to come. All right. So yeah, so there's no point discussing. So I in the different groups today as well, it's been all about this paper that was apparently leaked. We can't be sure about that as of now. But again, it's not in our control. There's nothing that we can do about it. Focus on what is in your control. Okay. And if something like this happens for any of the other papers later on for maths and for any other subjects, please try that you do not become a part to it. Okay. So a lot of you are thinking right now, and rightly so, that maybe it was unfair to you if it was actually leaked. So if unfortunately it happens for another paper later on, make sure that you're on the right side and you're not a part of spreading a leaked paper like this, and you instead report it as soon as you hear of something like this. Okay, so just like you do not want an unfair disadvantage, you would also you should also not want an unfair advantage. Okay. But in any case, what had to happen has happened. Forget about that, or at least leave that on the side for now and focus on the remaining papers. Okay, all right. So let's have a look at this paper now. June 2022, paper 5, variant 1. Okay, so I think I'll quickly go over this question as well. It's not that difficult, but some people are asking about this. So I'll just quickly go through this as well. It says there are 6 men and 8 women in a book club. The committee of the club consists of 5 of its members. Mr. Lan and Mrs. Lan are members of the club. In how many different ways can the committee be selected if exactly one of Mr. Lan and Mrs. Lan must be on the committee? Okay, so how many people do we have to select? 5 members. Out of how many? Out of 14. And the only condition is that it should either be Mr. Lan on the committee or Mrs. Lan on the committee. One of them, and exactly one of them, must be on the committee. Now, let's consider 2 scenarios. One scenario would be that you have Mr. Lan on the committee. Okay, how many people do you have to select? You've got to select 5 people. If Mr. Lan is selected and Mrs. Lan is not selected, this is one possibility. In how many ways can you do this? You have 14 people in total. About these 2 people, you have already decided that Mr. Lan should be there and Mrs. Lan should not be there. Now, what is the choice about? Out of 14 people, you're left with 12 people. And from those 12 people, how many more do you need to select? You needed 5 people in total. You have already selected one of them. That's Mr. Lan. You want 4 more, so that will be 12C4. Okay, that's one possibility. Make sense? That Mr. Lan is selected and Mrs. Lan is not selected. And then the other possibility would be that Mr. Lan is not selected and Mrs. Lan is selected. That's the other possibility. In how many ways can we do that? Again, the remaining people are 12. Out of those 12 people, we have to select 4. That's 12C4. You can evaluate each one of them separately. 12C4, that's giving me 495. And now it's either the first case or the second case. You add these 2 cases up together, and that gives you the result. In this case, this is going to be 990. Okay, that's the first part. Let's look at the next part now. It says, in how many different ways can the committee be selected if Mrs. Lan must be on the committee and there must be more women than men on the committee? Now, Mrs. Lan must be on the committee. So we can basically think of it like this, that Mrs. Lan is already selected. Amongst those 5 people, Mrs. Lan is already there. She is already one of those 5 people. So she's already selected. Okay, now if she's already selected, let's think about the remaining people. Let me write that down here. Mrs. Lan, she's selected already. She's one person. And now they're saying there must be more women than men on the committee. How many men do we have in total? We've got 6 men in total. How many women do we have in total? 8 women in total. However, one of them is Mrs. Lan, and she's already selected. So we have a choice about the remaining 7 women now. Remember, we have to select 5 people in total, right? We have to select 5 people in total. Mrs. Lan is already selected. And what we want is, we want more women than men on the committee. Now, what are the possible cases you could get for that? So this is one person already selected. Let me actually write that here. One person already selected. I think we just rearrange this as well, so it becomes easier to understand, because Mrs. Lan is already one woman selected. One possibility could be that you have the remaining 4 people, all women, and no men. That is possible, right? Is there any condition that says there must be at least one man? No. So this is possible that you have all women. In how many ways can you do this? 7C4 into 6C0. Okay. Then another possibility could be out of 7 remaining women, we select 3 more, and out of remaining 6 men, we select 1 more. What would that be? That will be 7C3 multiplied by 6C1. And then finally, we could have 2 women and 2 men. Still, the number of women will be more because Mrs. Land is a woman, plus 2 other women. That's 3 women in total. That's more than the number of men. In how many ways can we do this? 7C2 into 6C2. If you want, you can also multiply 1C1 with each of these cases, right? That you have 1 Mrs. Land and you're selecting 1 Mrs. Land. But it's not necessary because 1C1 is just 1. You can just ignore that as well because she's already selected. Out of the remaining people, we're saying we have to select this many for each case. Now we can find the number of possibilities that we get for each of these cases and then just add them up together. Let's see what we get for the first case, 7C4, that is 35. And then 7C3 is also going to be 35, I think. And then you have 7C2 multiplied by 6C2. Sorry, there was also 6 there. 7C3 multiplied by 6C1, which is a 6, that's 210. And then 7C2 multiplied by 6C2, which gives us 315. We add all of these cases and see what that gives us. What do we get from this? 35 plus 210 plus 315, that's giving me 560. So the total number of possible committees that we get from this is 560. And that's your final result. Okay? Make sense to everyone? All right, good. Let's move on to the next one now. Question number 3, most of you are saying is easy. Yeah, so nobody has asked about that. So let's skip that. Question number 4. Okay, let's have a look at this now. It says Jacob has 4 coins. One of the coins is biased such that when it is thrown, the probability of obtaining a head is 7/10. He has 4 coins in total. One of them is biased. And the probability of head for that coin is 7/10. The other 3 coins are fair. Fair means they have equal probabilities of heads and tails. Jacob throws all 4 coins once. The number of heads that he obtains is denoted by the random variable x. The probability distribution table for x is as follows. Show that a equals 1/5 and find the values of b and c. Okay, now how can we do this? We need to find the probability of getting 1 head, right? Because that it says the number of heads is what they're calling x. Okay. Now, how do you think about this? We need to find the probability of getting 1 head, 2 heads, and 3 heads. How do you find each of those 3 cases? Let's think about this. There are 4 coins. How can you get 1 head? 1 head is possible if the first one is a head, the second one is a tail, the third one is a tail, and the fourth one is also a tail. Right? Now we are assuming the first coin is the biased one, and then the remaining ones are fair. What would be the probability that you get in this case? So for now, what we're doing is probability of x being equal to 1. How can we get 1 head? All right, that's what we're trying to find out. If the first one is heads, what's the probability of that? Probability of the first one being heads is 7/10. And then for the remaining 3, the probabilities are 1 over 5 for each of them. So 7 over 10 into 1 over 5 into 1 over 5 into 1 over 5, you can say that's 1 over 5 raised to the power, sorry, why 1 over 5? 1 over 2. 1 over 2 raised to the power 3, right? Because 1 over 2 into 1 over 2 into 1 over 2, that will just be 3. Now, that's one possibility. Then another possibility could be that the first one is a tail and the second is a head, the third is a tail, the fourth is a tail. What would you get in that case? If the first one is a tail, what's the probability for that? 3 over 10, right? That's the biased point. And then the probability for the second one being heads and the third being tails and the fourth being tails, they're all the same because they're fair coins. These probabilities are all the same. It's going to be 1 over 2 into 1 over 2 into 1 over 2. That's 1 over 2 raised to the power 3. And if you think about it, you're going to get the same result from TTHT as well, and also TTTH. All of them are going to give you the same result. This one that we had for the last case. You can add these cases together and you would get the result. Okay, you can see what this turns out to be. What's this number? 1 over 5? Yeah, so it should turn out to be 1 over 5. That's what they wanted from us eventually. So this turns out to be 1 over 5. And that's the value of A that we were looking for, right? That's A. That's what we had to find in the first part. Okay. Now, what about probability of getting 2 heads? Let's think about that case now. When you have 2 heads, how can you get 2 heads? How is that going to be possible? It could be that the first one is heads and the second is tails. First is heads, or let's actually do it like this: heads, heads, tail, tails. Now you can think of how many total possibilities there are going to be for this. If you remember your permutations well, in how many ways can you arrange these 4 letters? 4 factorial over 2 factorial and 2 factorial. There are going to be 6 cases for this one now. Okay? For this one, you would have 6 cases. Now, that will be a lot to list down. So let's actually think about how we can, just like we did for the previous case, we had 3 cases that were the same, and then 1 case that was different. We could do something similar here as well. Okay, HHTT, what's the probability for that? 7 over 10 for the first one. And then for the remaining, we have 1 over 2 whole cube, right? Because these are all fair coins. And then what are the other possibilities? With the first being head, the remaining coins could be tail, head, tail, or they could be tail, tail, head. All of these are going to be the same, right? Because only the first one is biased. So if the first is head, the probability of first is 7 over 10. The probability of the second, third, and fourth, they are all 1 over 2. So they're all the same. What we can do is we can just multiply this probability by 3 because we have to add it 3 times. We say, let's just multiply this by 3. Okay, that will give us this probability. And then another possibility could be that the first one is a tail, the second is a tail, and we have head and head. With the first being tail, how many possibilities do you have? For the second, third, and fourth, you could have tail, head, tail, head, and you could also have tail, head, head, tail. Now, for this one, if the first coin is the tail, the probability for that is 3 over 10. And for the remaining ones, we've got 1 over 2 whole cube. And now it's going to be the same for all of for both of the other cases as well. So we multiply this by 3 as well. That's going to give us a result. We add these 2 cases together, and that will be the probability of x being equal to 2. And that will be the value for b. Okay, you can see what this turns out to be. 0.5 raised to the power 3 multiplied by 0.7 multiplied by 0.3. So the first one is turning out to be 0.2625 for me. And then 0.3 into 0.5 raised to the power 3 multiplied by 3. The second one is 0.1125. You add these two cases together. And that gives us 3 over 8. Yeah, so that's what we get. 3 over 8 from this. This is what we get for the value of B. Okay. So this was A. And now this is B. And then we've got the last case when we want 3 heads. Now that's straightforward. Once we've got the values of A and B, how can you find C? The total probability is going to be 1. So we subtract from 1 all of these other numbers now. So we know the value for A. The value of A is 1 over 5. The value of B is 3 over 8. C can now be found like this. We can say C equals 1 minus 3 over 80. That's the probability of 0. Minus 1 over 5, the probability of X equals 1. And then 3 over 8, the probability of X equals 2. And 7 over 80. And that will give you the value for C. Or you can do it directly as well if you want. You can make 4 cases for that as well. And you get the result for that. Okay, let's see what this turns out to be. 1 minus 3 over 8 minus 1 over 5 minus 3 over 8 minus 7 over 80. And that's giving me, let's check this again, 1 minus 3 over 80 minus 1 over 5 minus 3 over 8 minus 7 over 80. That's 3 over 10. Okay, so for C, I'm getting 3 over 10 or 0.3. That's the value that we've got for C here. Is that okay? Can somebody confirm this as well? Right? Okay, good. Now we need to find the expected value of X. How do you do that? For this, you just have to use the formula sigma XP. I'm sure you can all do that. Right? This part is straightforward. Expected value of X is just sigma XP. You can evaluate this. You've got the probabilities, you've got the values of X, multiply them together, and then add them up together. You will get the result. Okay, what's the result for expected value of X? That's giving me 11 over 5, right? 11 over 5. It's just a 1 marker, so you can just write down the answer directly as well, and that's okay. In decimals, that's 2.2. Okay, you can just do this on your calculator directly. Just multiply all X and P's and then add them up together to get the result. Make sense? Now let's move on to the next one. Now it says Jacob throws all 4 coins together 10 times. Now he's repeating the same thing over and over again. He's doing that 10 times in total. Find the probability that he obtains exactly 1 head on fewer than 3 occasions. Now, what kind of distribution is this? You've got something repeating, and they want the probability that he obtains exactly 1 head on fewer than 3 occasions. It's a binomial distribution because we can say obtaining exactly 1 head, if this is what we're calling success, when he throws 4 coins once and he obtains exactly 1 head, if we call that a success, what's the probability that out of 10 times he gets fewer than 3 successes? Okay. Now, what's the probability of success? Probability of obtaining exactly 1 head. We know that from the previous part. The probability of obtaining exactly 1 head is 1 over 5. So that's the probability of success that we have in this part. What about the probability of failure? That will be 4 over 5. And now since it's binomial distribution, let's use the formula for binomial distribution. For x less than 3, fewer than 3 occasions means x has to be less than 3. We need to find the probability of that case. Now in binomial, we don't have a formula directly for inequalities. We have to break it down and say x less than 3 means you have either 0 successes, or you have 1 success, or you have 2 successes. You find the probabilities of each of these 3 cases, add them up together, and that is going to give you the result. What's the formula for binomial? It's NCR p raised to the power r q raised to the power n minus r. Just input values in this. Now, we know that the value of n is supposed to be 10 here, right? Because we're repeating this thing 10 times. The value of n is 10. So we have 10C0 into p, which is 1 over 5 raised to the power 0, into 4 over 5 raised to the power 10 minus 0, which is 10, plus 10C1 into 1 over 5 raised to the power 1 into 4 over 5 raised to the power 9, plus 10C2 into 1 over 5 raised to the power 2 into 4 over 5 raised to the power 8. And that is going to give you the result. You can evaluate this and see what that turns out to be. Does anyone have the result for this? It's 0.8 raised to the power 10 plus 10 into 0.2 into 0.8 raised to the power 9 plus 10 C2 multiplied by 0.2 raised to the power 2 and 0.8 raised to the power 8. Okay, so I'm getting 0.67779 for this. 0.6777995. So if you were to round it off, you would say this is 0.678. That's the probability that we get in this case. All right. That's your part C here. Let's move on to part D. It says find the probability that Jacob obtains exactly 1 head for the first time on the 7th or 8th time that he throws the 4 coins. Okay, now what kind of distribution is this now? That he obtains exactly 1 head for the first time. Does that remind you of something? Something happening the first time? You getting your first success? That's geometric distribution, right? And the conditions for that geometric are also satisfied. The probabilities are remaining constant. They're not changing across the repetitions. There are 2 outcomes, success or failure, because we are saying this is success, obtaining exactly 1 head. The probability of that is 1 over 5, and the probability of failure is 4 over 5. Now we want to find the probability that he obtains exactly 1 head for the first time on the 7th or 8th time that he throws the 4 coins. Now it's geometric distribution. In this geometric distribution, what we are looking for is probability of x being equal to 7 or probability of x being equal to 8. Any one of these 2 cases. So if we find those 2 probabilities and then add them up together, what's the formula for geometric distribution? It's q raised to the power r minus 1 times p. That's what we're going to use here. Q is 4 over 5. 4 over 5 raised to the power 7 minus 1, which is 6, into p, which is 1 over 5, plus 4 over 5 raised to the power 7 raised to the power 1 over 5. And that should give you the result. You can see what that turns out to be. 0.8 raised to the power 6 into 0.2 plus 0.8 raised to the power 7 into 0.2. And that is giving me 0.09437. 0.09437 I can say that's 944. So 3 significant figures, and that's our final answer for this word. Okay. Now let's move on to the next one. So the next question that you're asking about is question number 5 from this paper. Have a look at the other paper as well, and let me know the questions that you find difficult from that paper. From 5.3. Okay, let's try this one now. Question number 5. It says the lengths in centimeters of the leaves of a particular type are modeled by this distribution. N 5.2 and 1.5 square. Remember, in this notation, what are these values? 5.2 is the mean and 1.5 squared is variance. Okay, variance is denoted by sigma square. Find the probability that a randomly chosen leaf of this type has length less than 6 centimeters. Now, this is simple normal distribution, right? If you're saying lengths are denoted by x, we want to find the probability that x is less than 6. It's normal distribution. We convert it to z first of all. It becomes z less than 6 minus mu, which is 5.2, divided by sigma. Sigma in this case is 1.5. So we divide by that and see what that gives us. Probability of z less than 0.8 divided by 1.5, and that's giving me 0.533 to 3 decimal places, because the values of z in the table are correct to 3 decimal places. Now, if it's the standard form already, z less than a positive number, we can find this value directly from the table, and that will give us the result. Okay, let's do that. 0.533. Let's find this value in the table. All right, 0.533. What do we get for this? 0.7019. Then we have to add 10 at the end. That becomes 0.7029. Okay. Let's write that here. 0.7029. That's the probability that we were looking for in the first part here. Okay, you can just leave it like this. That's your final answer. Okay, now it says the lengths of the leaves of another type are also modeled by a normal distribution. A scientist measures the lengths of a random sample of 500 leaves of this type and finds that 46 are less than 3 centimeters and 95 are more than 3 centimeters long. Find estimates for the mean and standard deviation of the lengths of leaves of this type. Now, the mean and standard deviation are missing, and we've got some information about probability. This is inverse normal, right? What information are we given? When they took a sample of 500 leaves, they found that 46 are less than 3 centimeters long. So we can say the probability of a leaf being less than 3 centimeters long is what? 46 out of 500. Right? The relative frequency concept that we've done in O levels as well. Probability can also be thought of as relative frequency. So 46 are the favorable outcomes divided by the total number of outcomes, 500. We say the probability of x being less than 3 is equal to this. 46.500, you can see what that is. That's 0.092. Similarly, they're saying the probability that a leaf is more than 8 centimeters long, that means probability of x being greater than 8, that is equal to 95 over 500. That gives us probability of x being greater than 8. That's 95 over 500. That's 0.19. And now this is inverse normal. You convert it, you write this in terms of z first of all, find the values of z, and then put them in the equation z equals x minus mu or sigma. You'll get two equations, simultaneous equations, solve them simultaneously, and you would get the result. So how do we apply by inverse normal distribution? We say, let's write this in terms of z. X less than 3 is less than is basically 0.092, the probability of that. We can say z less than some value, this probability will be 0.092. And now we need to figure out whether this z value is positive or negative. How do you do that? You think of the normal distribution curve. This is what the curve looks like, roughly. Since it's a z distribution, we have 0 in the middle. Is z going to be placed on the negative side or the positive side? The area to the left of z is smaller than 0. So how do you think about this? Less than means we are looking at the left side. The area to the left is supposed to be smaller than 0.5. How can the area to the left be smaller? If we place z here, the area to the left would be larger. We don't want that. If we place z here on the left side, on the negative side, that is when the area to the left side would be smaller. That means z is supposed to be a negative number. So z is a negative number. That's what we understand from this. Z is supposed to be negative. And we're given that this area is 0.092. Now, this is not standard form then. How do you convert it to standard form? You can see this is the same thing as saying the area to the right of this positive z value. This is 0.092. And then if that is 0.092, what about the area to the left of this positive z value? This will be 1 minus 0.092. If this area is also 0.092, the area to the left is 1 minus 0.092. What does that give us? 0.908. So we could write that as probability of z less than the positive value of z, that equals 0.908. Now, this is the standard form. We can go and look for the value of z in the table now. The probability is supposed to be 0.908. Let's find the corresponding z value to this probability. 0.908, where is that? Let's find that probability, 0.908. Let's write that inside, 0.908. Okay, this is the number that I have here in the table. That's slightly smaller than that. The immediately smaller number than 908. 908 means 9080. Okay. Now, what value do I get corresponding to this for z? 1.32. But that's the value of z corresponding to 0.9066. What's the difference between them? 14. So we need to add 14 more to it. We go to the right side. Do we have 14 here? Yes, this is 14. We take 9 from here, and the value of z therefore becomes 1.329. That's the value of z that we use here, 1.329. Let me go back there. And now we say the positive z value is 1.329, but actual z was supposed to be negative. So we say the actual z value, which was a negative value, that is equal to 1.329. Okay. Now that we know this, now put this in the formula. Z equals x minus mu over sigma. So that's minus, I'm sorry, this is negative. Let's put negative here. Minus 1.329, that equals x. In place of x, we've got 3 here. Minus mu over sigma. This is one equation that we've got. Now, using the same method, we would derive another equation from this. How do we do that? We say probability of z greater than something, that is equal to 0.19. And again, we think of the area to the left or right. In this case, we're looking at the right side. because of this greater than sign, the area to the right should be smaller now. If the area to the right is smaller, where is Z going to be placed now? Z is going to be placed on the positive side now, because the area to the right is supposed to be smaller. So now Z is going to be placed on the positive side. So Z is now supposed to be positive. And we're given that the area to the right of Z, that's this area is 0.19. Now, this is not standard form as well. If the area to the right of Z is 0.19, what about the area to the left of the Z value? We can say probability of Z less than this positive value of Z, that is 1 minus 0.19. This region is 0.81. We have 0.81 here. And now we can go to the table, find this value of Z from that, corresponding to 0.81. Probability is 0.81 now. So 8100, let's look for that value. The immediately smaller value from than that is this 0.8078. The corresponding Z value that I'm getting from this is 0.87. And that value is corresponding to 8078. Let's find the difference, 22. Now we go to the right and find 22 here. This is 22. And that gives us 8 as the third decimal place. So 878, that's the Z value that we're getting from this, 0.878. Let's write that here. The positive Z value turns out to be 0.878. And the actual Z is also supposed to be positive. So we say Z is 0.878 now. Now let's input this in the formula as well. 0.878, that's Z equals X, which is 8 here, minus mu over sigma. You've got two equations. You solve these two equations simultaneously, and that is going to give you the result. Okay. Now, how do you solve them simultaneously? It becomes minus 1.329 sigma equals 3 minus mu, and mu is equal to 3 plus 1.329 sigma. From the other equation, we get 0.878 sigma equal to 8 minus mu. Mu equals 8 minus 0.878 sigma. Now we equate both of them, and that gives us 3 plus 1.329 sigma equal to 8 minus 0.878 sigma. And that's going to give us the value for sigma. Let's see what that turns out to be. 5 divided by 8 minus 3 is 5, right? 8 divided by 1.329 plus 0.878. And that's giving me sigma equal to 2.2655. That's the value of sigma that I'm getting. Now we put this value of sigma back in the mu equation. We can put that here or here in any of them. What's the value of mu that we get from this? Mu equals 3 plus 1.329 multiplied by 2.2655. And that should give us the value for mu as well. This multiplied by 1.329 plus 3, and that's 6.011. Mu is equal to 6.01. That's what we were looking for. We've got the value of mu and standard deviation, which is 2.27 if you want to round it off. That's what we get. Okay, we found the values of mu and sigma. That's a standard inverse normal problem. Now, it took some time, but there wasn't any complication as such. As long as you understand inverse normal well, that's all that you have to do here. Now it says, in a random sample of 2,000 leaves of this second type, how many would the scientist expect to find with lengths more than one standard deviation from the mean? More than one standard deviation from the mean. Now remember, when they talk about number of standard deviations away from the mean or within the mean, we can think of this in terms of Z directly. So rather than thinking about variable x, it's easier to think of z directly because we know z is a distribution for which the mean is equal to 0 and standard deviation is 1, right? So if the lengths have to be more than 1 standard deviation from the mean, let's think about this. Mean is in the middle. For a z distribution, mean is 0. You want to be more than 1 standard deviation away from the mean. On the left side, you would have -1. On the right side, you have 1. This is 1 standard deviation away on both sides. You want to be more than 1 standard deviation away. That means you either want to be in this region or you want to be in this region, right? In the middle, you've got 0. This is 0, which is actually the mean. 1 standard deviation for z is 1 unit. If you want to be more than 1 standard deviation away from the mean, what that means is z should either be less than -1 or it should be greater than 1. These are the two possibilities that you've got. This is the probability of one leaf being one leaf having a length that is more than 1 standard deviation away from the mean. Then once we find the probability for 1, we can just multiply that by 2000 to find the expected number. But for now, let's find the probability of one leaf satisfying that criteria. Okay. So more than 1 standard deviation away from the mean, what does that mean? It's either less than -1 or greater than 1. Z less than -1 or Z greater than 1. Now, if you think about it, this is what the normal distribution looks like, roughly. For Z distribution, you have 0 in the middle. If you have -1 here and you have +1 here, what you're looking for is this region and this region. Now, since the curve is symmetric, these two regions are both going to be the same. We can just find one of these and just multiply that by 2. Okay. So which one do we find? Let's find the right one. That's easier. Z greater than 1, we could say that's the same thing as saying probability of, in fact, we could say 1 minus probability of Z less than 1, right? So find the area to the left of 1, subtract that from 1, and that will give you this region. And now it's standard form. You can go to the table, find this probability and see what that turns out to be. Z less than 1. So corresponding to a Z value of 1, what's the probability that we get? It's 0.8413. 0.8413. What's the result that we get from this? 1 minus 0.8413. This is 0.1587. If this region is 0.1587, this yellow region, that means the other one is also going to be 0.1587. So what's the total probability? This one would also be 0.1587, right? Because the curve is symmetric. They're both supposed to be the same. So the total probability turns out to be 2 times 0.1587, or you could say 0.1587 plus 1.87. That gives it the same thing. The probability turns out to be 0.3174. So for one leaf, to satisfy the criteria, the probability is 0.3174. Now, if you had 2,000 leaves, how many of them would you expect to satisfy this criteria? Just multiply this number by 2,000. 2,000 into 0.3174. What do we get from that? 634.8. But since we're talking about number of leaves, that has to be an integer. We can't write a decimal here. Let's round it off and it becomes 635 because we're talking about number of leaves. Right? They're saying how many leaves would the scientist expect to find with these lengths out of 2,000? So we say 635. And that's our final answer. Make sense? That was question number 5. No problems? Okay. Why did we take 635 and not 634? Well, we just rounded off 634.8. We are saying this is the expected number. If we round it off, it becomes 635. So we write 635. But generally, marking schemes for such questions, they allow both 634 and 635. But 635 makes more sense because that's what we get when we round it off. Okay. All right. Now let's look at the next one. So the next one that you've asked about is question number 6. Okay, let's try that. Question number 6 from this paper. Okay, Janice is playing a computer game. She has to complete level 1 and level 2 to finish the game. She's allowed at most 2 attempts at any level. For level 1, the probability that she completes it at the first attempt is 0.6. If she fails at her first attempt, the probability that she completes it at the second attempt is 0.3. If she completes level 1, she immediately moves on to level 2. Okay, that's a lot of information to process. Let's break it down and read it step by step. Okay, so she has to complete level 1 and level 2 to finish the game. There are 2 levels. She's allowed at most 2 attempts at any level. Okay, so for level 1 as well, she has 2 attempts. For level 2, she has 2 attempts. Okay. For level 1, the probability that she completes it at the first attempt is 0.6 for level 1. If she fails her first attempt, the probability that she completes at the second attempt is 0.3. If she completes level 1, she immediately moves on to level 2. Okay. For level 2, the probability that she completes the first attempt is 0.4. If she fails at her first attempt, the probability that she completes at the second attempt is 0.2. Show that the probability that she moves on to level 2 is 0.72. Now, how can she move on to the second level? She either completes the first level in the first attempt. What's the probability for that? 0.6 that she completes it on the first attempt, or she completes the first level on the second attempt. In that case, we can say she fails the first attempt, that's 0.4, and then she is successful in the second attempt, that's 0.3. We multiply these two, and that should give us the result 0.6 plus 0.12, and that's 0.72. Now, it might make this easier if you draw a tree diagram first. That will make things a lot easier, okay? That will help you with the other parts of this question as well. So let's actually draw a tree diagram for this as well. They have not asked us to do that explicitly here, but if you do that once, that will help you with the rest of the calculations. Let's make a tree diagram for this. Let's do that in the second part. And that will make it, because we have more space here. Now, what are the possibilities? When she starts doing level 1, she either is successful in her first attempt or not successful. So let's say she either completes it or does not complete it. Or you can say, let's say she is successful or she fails the first time. Now, if the probability of her being successful the first time, that probability is 0.6. The probability of failure, therefore, would be 0.4. If she is successful at the first attempt, what happens? She moves on to the second level. And at the second level, she can either be successful or she can fail. Right? We'll talk about what happens afterwards in a moment. Let's consider this scenario, because here we are still at level 1. If she fails at level 1, on the second attempt, she can either be successful or she can fail. If she fails both attempts, the game ends there because she has only 2 attempts for each level. What are the probabilities associated with this one? For the second attempt, the probability of success is 0.3, and the probability of failure then would be 0.7. Let's actually stick to this for now. This is first level done. If she's here or here, she moves on to the second level. Now, in the second level, she has 2 attempts again. She can either be successful or she can fail in her first attempt. What are the probabilities of success and failure in the first attempt? In level 2, 0.4 and 0.6. This is 0.4 and this is 0.6. 0.4 and 0.6. If she is successful, the game stops there as well, right? She has completed both levels and the game finishes. If she fails at the second level once, she has another attempt. She can either be successful in that second attempt or fail in that second attempt. Again, here, she can either be successful in that second attempt or fail in that second attempt. What are the probabilities here? On the second attempt, probability of her being successful is 0.2, and the probability of her being her failing is 0.8. So we have 0.2 here and 0.8 here. This is what the tree diagram looks like. Now, let me actually color code it a bit so you can understand what is representing what level. So this is level 1. The blue part is level 1. And then the red part is level 2. Okay? Blue part is level 1 and red part is level 2. Okay? Now it says find the probability that she finishes the game. Finishing the game means that she completes both levels eventually. Now, what are the possible cases for that? She's successful here and successful again. She's successful the first time and then fails and then is successful. Or she fails the first time and then is successful and then is successful. She fails the first time, then is successful and then fails and then is again successful. These are 4 pathways that we've got. We find the probabilities for each of these paths and then add them up together. Okay, and that's going to give us the result. Let's see what this turns out to be. Let's look at the first path here. That's 0.6 into 0.4. Let me actually write that alongside here as well. The first part is that she's successful and successful. Then the second part, she's successful in the first level and then failed and then is successful. What's that probability? 0.6 into 0.6 into 0.2. And then the third part is fails, success, success. FSS. What's this? 0.4 into 0.3 into 0.4. And then finally, she fails and then is successful, then fails again, then again successful. And that gives us 0.4 into 0.3 into 0.6 into 0.2. So once you've made the tree diagram, it makes it quite straightforward after that. Okay, but making the tree diagram here was slightly tricky. That's the tricky part. Once you're done with that, the rest of it is not that complicated. And now you can evaluate this and see what that turns out to be. Okay, let's evaluate this. 0.6 into 0.4. Again, can somebody do this for me as well? To confirm this, 0.6 into 0.4 plus 0.6 into 0.6 into 0.2 plus 0.4, 0.3 into 0.4 plus 0.4 into 0.3 multiplied by 0.6 multiplied by 0.2. Yeah, so that's what I'm getting, 0.3744. That's the probability that we got for this, 0.3744. And that's our final result for this part. Okay. And then it says, find the probability that she fails exactly one attempt given that she finishes the game. Now, what kind of probability is that? That is conditional probability. Okay, now how do we think about this? Probability, now that you have structured it well in the previous part, that would be very helpful for you in the last part now. Probability that she fails exactly one attempt, given that she finishes the game. That's the probability that we want to find out. Now, that's conditional probability. What's given is going to be the denominator. So in the denominator, you've got the probability that she finishes the game. And in the numerator, there is the probability that she fails exactly one attempt. And along with that, she finishes. Both of those conditions are true in the numerator. Now, do we know the denominator already? That's exactly what they made us find the previous part. Probability that she finishes the game, that's 0.3744. That is going to be the denominator here. Now, what about the numerator? That she finishes the game, and while she finishes the game, she fails exactly one attempt. Now, look at these four cases that we had. Now, they're going to be helpful here for us since we wrote them down. In how many of these she's failing exactly one attempt? In the second case and in the third case. We just consider these two cases for the numerator here. Okay. Now, what are these two cases? Let me just evaluate these here separately. That will make things easier for the next part. 0.6 into 0.4. This is giving me 0.24, the first probability, and then 0.6 into 0.6 into 0.2. This was 0.072, and then the next one was 0.4 into 0.3 into 0.4, and this one is 0.048. The final one, 0.4 into 0.3 into 0.6 into 0.2, that is 0.0144. These are the two cases that satisfy both criteria, that she's finishing the game and she's failing exactly one. That is what you would have in the numerator here. What's the total probability for those two cases? 0.072 plus 0.048. This is the total probability where both of these conditions are met. And that is going to give us the result 0.072 plus 0.048 divided by 0.3744. And that's giving me the conditional probability. That's 25/78. Or in decimals, that's 0.32051. Or we can say that's 321. That's the probability, the conditional probability that we were looking for. Is that okay? Make sense to everyone? And that's it. That was the last part of this paper. Now let me know if you have any problems in the second paper, paper 5.3. We could quickly have a look at that as well. For now, I don't have many votes for the questions from the second paper. So maybe you can have a look at that paper quickly. Let me know what the questions you have. We could have a look at some of them as well. This was June 2022, paper 5, variant 1. Now, the next paper that we want to do is June 2022, paper 5, variant 3. It's not working for me. June 22, paper 5, variant 3. That's the other variant now. Let's do the difficult questions from this paper quickly as well. June 22, paper 5, variant 3. Now, which ones do you want to do from this paper? Let me know in the poll that's posted on the WhatsApp group quickly. I'll have a look at the questions myself as well because of the low strength today. Many people are probably disappointed after the P1 exam today and after all the rumors that we have about that. So what I'll do is I'll actually just choose some questions myself as well because I don't see many votes on the poll yet. So let me quickly go through this. The first one is about cumulative frequency graph. I suppose you can do that. Then you have to find 20th percentile, and find the mean of these heights, find the median of these heights. Okay. Give a reason why median is likely to be more suitable. There would be some extreme value. Remember, you have to specify extreme value. Don't just write that there's an extreme value. Specify that this is an outlier. This is 19.4 is an outlier. That is why median is more suitable. Then you have question number 3. Okay, does not look that difficult. 4. This is geometric distribution, the first part. And then second part is also geometric for 10 randomly chosen throws. This is binomial then. Okay. So you have no problems in this as well. Apples that weigh between 142 grams and 205 grams are sold to a supermarket. Their mean standard deviation is given. Okay, so probability of being sold to the supermarket. So they have to weigh between 142 and 205 grams. So you have to find the probability of an apple weighing between these two numbers. Okay, that's simple normal distribution. Okay, now this looks slightly complicated. Question number 5. Let me come back to that in a moment. No one has asked about that, but I think we could have a look at that one question. Then it says Sargent is practicing for a long jump competition. He counts any jump that's longer than 6 meters of success. So the tree diagram and one success, given that he has at least one success, with conditional probability. Or okay. And then you're asking about question number 7 from this. Okay, let's do 2 questions from this paper, questions 5 and questions 7. Okay, these are the 2 questions that we want to do from this paper. June 22, paper 5, variant 3. Let's do 2 questions for this, questions 5 and 7. Let's start with this one. It says, Farmer Jones grows apples. The weights in grams of the apples grown this year are normally distributed with mean 170 and standard deviation 25. So we have the mean given and we've got the standard deviation given. Apples that weigh between 142 grams and 205 grams are sold to a supermarket. Find the probability that a randomly chosen apple grown by Farmer Jones is sold to the supermarket. Now, an apple is going to be sold if it weighs between these two numbers, 142 grams and 205 grams. So we want to find the probability that the weight, if we denote that by X, that's between 142 and 205. This is the probability that you want to find out. Now, how do you do this? You convert it to Z first of all. This is simple normal distribution. Apply the Z formula on this. X minus mu over sigma. That means Z is between 142 minus mu. Mu is 170 divided by the standard deviation, which is 25. and 205 minus 170 divided by 25. What do we get for z here? We get z between minus 28 divided by 25, and that's minus 1.12, and 35 divided by 25, that is 1.4. So z is between these two values. We have to find this probability. How do we do that? Let's think of the normal distribution curve, how it's going to look like. This is what the normal distribution curve looks like, roughly. So you would draw a rough curve like this, and then you have 0 exactly in the middle. That's the mean of the z distribution. 1.4 is going to be on the right side, and minus 1.12 is going to be on the left side. What we are looking for is the area between these two numbers. This is the area that we want to find. Okay. Now, how do you find this shaded region? It's an interval. It's a two-sided interval. One of those values is negative and the other is positive. Now, this is a standard case that you should learn when you do normal distribution. So it should be nothing new for you. All you have to do is find the total area to the left of 1.4. So you could say it's the same thing as saying probability of z less than 1.4. That's all of this region. But the problem with that is it will also consider this region. We don't want that region, right? We only want the middle part. So from this total, we subtract the region to the left of minus 1.2. So probability of z less than minus 1.12, we subtract this probability from that earlier probability. Now, this is something that we can find from the table directly. Z less than 1.4, we can figure out this number from the table. Let's actually do that. Z less than 1.4, that's standard form, right? That's here, 1.4, that's 0.9192. This number is 0.9192. The problem is this other number. This is not standard form. Now we have to think of this again. Z less than minus 1.12. What does that mean? Let's focus on this part now. Again, you can think of another normal distribution curve for this. You don't necessarily have to draw this. You can think of it in your head as well. If you've done enough practice, you may be able to do it directly in your head. Otherwise, it's safer to just draw a normal distribution curve like this. Minus 1.12, that's going to be on the left side here. You want this region on the left side. How do you find that? First of all, you flip it. You say it's the same thing as this region on the right side. The area to the right of 1.12, that will be the same as this. But that's also not going to be standard form. Let me write that like this first. You can say this is the same as z greater than 1.12. We also can't find that directly. We say, let's find the region to the left of 1.12, subtract that from 1. So it's the same thing as saying 1 minus probability of z less than 1.12. And this is what we can find. We can say subtract from 0.9192 all of this region. And that is going to give you the result. Okay, now this is in standard form. This is in standard form now, z less than 1.12. We can go to the table and find the probability corresponding to this number and see what that turns out to be. 1.12. Let's go to the formula sheet. Okay. 1.12. Let me get rid of this first. (1.1) and then 2, we get 0.8686. Let's write that here. 0.8686, 1 minus this. And now we just simplify this whole thing, 0.9192 minus this whole thing. That is going to give us this probability that we're looking for. 0.9192 minus 1 plus 0.8686, and that's giving me 0.7878. That's the probability that a randomly chosen apple is sold to the supermarket in this case. Is that okay to everyone? Any problem with this? Yeah, that's what we were looking for, the probability. No questions? Okay, let's move on. Now it says Farmer Jones sells apples to the supermarket at $0.24 each. He sells apples that weigh more than 205 grams to a local shop at $0.3. Okay, so apples to the supermarket are sold at $0.24. Apples that weigh more than 205 grams, they are sold to a local shop at $0.3 each. And the apples that weigh less than 142 grams, they are not sold. The total number of apples grown by Farmer Jones this year is 20,000. Calculate an estimate for his total income from this year's apples. Now, how do you find this estimate? So we can actually divide this into three parts, basically. We can say one cutoff point is 142 grams, another cutoff point is 205 grams. An apple is either going to be in the region in the middle, in this region, or it's going to be in the region on the right side where it weighs more than 205 grams, or it's going to be in the region on the left side. Do we know the proportion of apples in each of these regions? We know the proportion for the middle region. We know the probability of an apple falling in the middle region, that's 0.7878. So the probability of being in the middle region is 0.7878. If you want to write this as a percentage, you can say 78.78% of apples fall in this category, in the middle region. Now, what about the ones on the sides? Can we figure those out somehow? Are we given any information about that? No. But have we found any of that in the working that we did in the first part? Okay, so this is what we found. The total region to the left of 1.4, that was 0.9192. And in fact, we also found this eventually. Let's use that instead. Probability of z greater than 1.12. That will be this region. Is that going to help? No, this one, in fact, I'm sorry. Let's focus here. Probability of z being less than minus 1.12. That's this region. That's the probability of an apple weighing less than 142 grams, right? Because the z value minus 1.12, it corresponds to 142 grams. So probability of being less than minus 1.12, what's that? We found that here. 1 minus 0.86.86. We can actually write this value here as well. So we can use that in the next part then. 1 minus 0.8686, this number was 0.1314. 0.1314. This is the proportion of apples that weighs less than 142 grams. So from this, we know 0.1314 is the proportion of apples in this region, 0.1314. And that is 13.14%. Okay? Can you find the remaining apples that fall in this category now? Yes, Faizan, you're right that we actually need the right side. But since we have the left side already, now figuring out the right side is going to be straightforward, right? Because otherwise we haven't found the right side separately earlier. We could actually get that by subtracting this number from 1 directly as well. That would work, yes. But this is another way of doing this, that you find the left-hand side and then subtract these two numbers from 1, okay? And see what the remaining number turns out to be. 1 minus 0.1314 minus 0.7878. And that's giving me 0.0808. But you're right, we could directly just do that from this 1 minus 0.9192. Because we don't even need this side. The left-hand side is not needed because these apples are not being sold at all, right? So they don't generate any income. So we just ignore those as well. So that's correct. Now, what do you get in this case? You get 8.08% of apples in this region. Now you know that the middle region, they are sold for $0.24. The region on the side, on the right side, they are sold at $0.3. How many apples do we have in this have in each region? Let's find this out. 20,000 multiplied by 0.7878. How many apples is that? 7,878 into 20,000. That is 15756 apples. And then do the same thing for this. 0.0808 multiplied by 20,000. That is 1616 apples. And now let's find the total income and see what that would be. For each of these apples in the middle, he's getting $0.24. 15756 multiplied by 0.24 plus 1616 multiplied by 0.3. And that's going to give you the result. You can see what that turns out to be. Okay, this is giving me $4266.24. This is the estimate of the income that he would generate. Now, I've shown a lot of working here because I'm explaining this, but you can also skip some of this, and that's okay. Make sense to everyone? No problems? Now, this was slightly tricky. The second part, now let's see what it says here. Farmer Tan also grows apples. The weights and grams of the apples grown this year follow this distribution. 72% of these apples have a weight more than W grams. Find the value of W. Now, this is simple inverse normal distribution. They forgot about the investment. Yeah, so this is so by income they mean the revenue he's generated. So it's not profits; it's basically the revenue, right? So sometimes income is used for revenues as well. It's not necessarily profits; it's just the revenues. Okay. All right. Now this is inverse normal. It's a normal distribution with mean 182 and standard deviation 20. 72% of these apples have a weight more than W grams. So probability of weight being more than W, that is equal to 0.72. That is what we're given. We need to find the value of W from this. This is simple inverse normal. We say, okay, Z greater than some value, that is equal to 0.72. Now, think of whether Z is going to be positive or negative. Greater means when we look at the right side, the area to the right side, that has to be larger than 0.5. When can the area to the right be larger than 0.5? Where are we going to place Z here? If we place Z on the negative side, the area to the right would be larger. If we place Z on the positive side, the area to the right would be smaller. So where do we place Z? Z will need to be placed on the negative side, therefore. So that means Z is a negative number. This is negative. So that's what we figured out. Z is negative. And all of this region, what's this? This is 0.72. Now, this is not standard form. How do we convert it to standard form? We can flip this and we can say, if the area to the right of Z negative, Z minus is 0.72, the area to the left of this positive value of Z, that is also going to be 0.72. So we can flip this and that gives us probability of Z less than the positive value of Z. That equals 0.72. Now, this is standard form. We can go to the table, find the value of Z corresponding to 0.72. Okay, so now probability is 0.72. Let's find that number here. 72 means 7200. This is the immediately smaller number. We say Z is 0.58. These are the first two decimals. And the number is 7190. What's the difference? 10. Go on the right side, this is 10. So the third decimal place is supposed to be 3. Z is 0.583 from this. So that means the positive value of Z is 0.583, but the actual Z was supposed to be negative. So we say Z is minus 0.583. And now we need to find the value of W. Let's put this in the formula. Minus 0.583 equals X, which is W in this case, minus mu. Mu was 182 divided by standard deviation, which is 20. And that is going to give you the value for W. You can see what that turns out to be. 20 into 0.583, and that's negative. So 182 minus that number, that's giving me 170.34. Yeah, so that's the value W that we get, 170.34. That's what we were looking for. Is that okay? That was simple. That was inverse normal. Okay, let's move on. So the next question that you're asking about in the last question is question number 7 from this paper. Let's try this now. Question number 7 now. This looks like permutations and combinations. Let's try this. A group of 15 friends visit an adventure park. The group consists of 4 families, Mr. and Mrs. Kenny and their 4 children. So these are 6 people in total. Mr. and Mrs. Liza and their 3 children. That's 5 people in total. Mrs. Martin and her child, that's 2 people. Mr. and Mrs. Nantes, they are 2 people. So that's 15 people in total. The group traveled to the park in 3 cars, one containing 6 people, one containing 5 people, and one containing 4 people. That's 15 in total. The cars are driven by Mr. Lizo, Mrs. Martin, and Mr. Nantes, respectively. In how many different ways can the remaining 12 members of the group be divided among the 3 cars? Okay, so there are no restrictions as such. And they have told us that Mr. Lizo is in one car, Mrs. Martin is another car, Mr. Nantes is in another car, and we know they're driving which car they're driving, right? Now, the remaining 12 people, they have to be placed in these 3 cars. Now, one can contain 6 people. One of them is the driver. He or she is already placed there. So the remaining 12 people, we have to select 5 of them to put in this first car that has 5 remaining places. So that's 12C5. And then the next car is going to contain 5 people. The driver is already there. So that's 4 remaining people. So we say out of the remaining 7 people now, place 4 in this car. And then how many people are we left with? 3. Place all of those 3 people in this remaining car. And that's going to give you the result. You can reverse the order as well. You could also say 12C3 into 9C4 into 5C5. That will also work. You can place people in any of the 3 cars first, and then second, and then second. Okay. So you can actually choose any of them, any order basically. It doesn't matter. So what do we get here? 12C5. Let's figure this out. 12C5 multiplied by 7C4 into 3C3, which is just 1. And this results in 27,720. Right? That's the first part. Fairly straightforward. This is all that you had to do here. If it was arrangements, yes. If it was arrangements, we would just do 12 factorial for that, because there are 12 remaining places and there are 12 people. There are no restrictions. We can place them in, we can arrange them in 12 factorial ways. Yes. If it was arrangements, that's what you would do. Okay. Now it says the group entered the park by walking through a gate one at a time. In how many different orders can the 15 friends go through the gate if Mr. Liza goes first and each family stays together? Okay, so they're basically going in a line, right? Let's say this is the gate. Let's say this is the front side. Mr. Lizo is going first. So let's call this person Mr. L, ML. This person is going first. So he is fixed here, right? He has to be in the front. And then each family has to stay together. Now, that means, first of all, we're going to have Mr. Lizo's family in front. How many people are there in his family? 5 people in total. So there are 4 remaining people. We say we have one box in which we have the 4 remaining people of Mr. Lizo's family. Let's call them L1, L2, L3, L4. Now remember, this box cannot move now because Mr. Lizo is in front and these 4 people have to be with him. So this box is fixed. In how many ways can you arrange the people in this box? 4 factorial ways. So we have 4 factorial for this. All right. And now we've got 10 people left. And there are 3 families. The families have to be together. So we say, you can actually do this on the side because I can't draw boxes here. Make it slightly neater. All right, so this is what it looks like. Mr. Lizo is fixed there in front. And then in the adjacent box, we've got the remaining 4 people from his family. And then we have 3 boxes. In one box, we have Mr. Martin and her child. Let's call them M1 and M2. Then in one box, we have Mr. and Mrs. Nantis. Let's call them N1 and N2. And then in another big box, we've got Mr. and Mrs. Kenny and their 4 children. That's K1, K2, all the way up to K6. We've got these 3 boxes on the left side now. Okay. Now, Mr. Lizo's family, they can switch places with each other in 4 factorial ways. What about these 3 families? These 3 families can also switch places with each other, right? So Mr. and Mrs. Kenny's family, they can come here as well. They can come here as well, right? They can switch places with each other. So these three boxes that we've got, they can actually switch places with each other. These boxes cannot move. The two boxes on the right side, they cannot move. But the three boxes that we have on the left side, they can switch places with each other as well. In how many ways can they do that? 3 factorial ways. 3 boxes, 3 factorial arrangements for those 3 boxes. And then within each of these boxes, people can switch places as well. So Mr. Kenny's family, in how many ways can they arrange? Can they be arranged? 6 factorial. Mr. and Mrs. N's family, Nanta's family, that's 2 factorial. And Mr. and Mrs. M's family, that's 2 factorial. And that should give you the result. Just multiply all of them. And yeah, that should give the result. Let's see what we get from this. 3 factorial multiplied by 6 factorial multiplied by 2 into 4 factorial. And that's giving me 414720. That's the result that you get from this. Make sense? No problems? Okay, good. That was part B. Now, okay, we have 2 more parts. It says, in the park, the group enters a competition which requires a team of 4 adults and 3 children. In how many ways can the team be chosen from the group of 15 so that 3 children are all from different families? A team has to be chosen. That's the combination now. We're not arranging objects now, arranging people now. We are selecting them. So there are 15 people in total, right? And they want a team of 4 adults and 3 children. In how many ways can the team be chosen from the group of 15 so that the 3 children are all from different families? Okay, now how do we think about this? We've got 4 families. We had this person M, they had 2 adults and 4 children. No, Mr. and Mrs. Kenny, they had 2 adults and 4 children. Mr. and Mrs. Liza, they had 2 adults and 3 children. And then Mrs. Martin and her child, that's 1 adult and 1 child. And then Mr. and Mrs. Nantis, they are both adults. Right? These are the people, these are the 15 people we have. Now, out of these 15 people, we want 4 adults and 3 children. There's no condition on the adults. How many adults do we have? 4, 7. There are 7 adults in total. Out of those 7 adults, how many do you want to select? 4, so that's 7C4. So selecting adults is straightforward like this. We just say 7C4, and that is going to give us the result. Okay? And now, what about the children? The 3 children have to all be from different families. Now, there are 3 families that have children. That means we have to select 1 child from Mr. and Mrs. Kenny's family. So there are 4 children there. We say, let's select 1 out of those 4 children. And then there are 3 children in Mr. and Mrs. Lizo's family. We say, let's select 1 out of those 3 children. Then we have 1 child here. We say, let's select 1 out of that 1 child. That's just 1. This is going to give you the result. You can see what that turns out to be. 7C4 multiplied by 4 into 3 into 1. And that's giving me 420. That's the result that we get. Okay? That's part C. Now let's look at the next one. It says, in how many ways can the team be chosen so that at least one of Mr. Kenny or Mr. Lizo is included? Okay, at least one of them has to be included. We could have both of them. That's also possible. But it's not possible that we don't have any of them. Okay, now one possibility is that we find the total and subtract from that the number of cases for when we do not have any of them, right? That is one possibility. Find the total number of combinations, total number of selections, subtract from that the number of selections when Mr. Kenny and Mr. Lizo are both not selected. Or we could make three cases when Mr. Kenny is selected, Mr. Lizo is not selected, and then Mr. Lizo is selected and Mr. Kenny is not selected, and then another case where both of them are selected. You can make three cases like that as well. If we do it either way, total minus both of them not being selected is going to be quicker. Let's do that. Let's do it that way. Total teams without restrictions. Total possible teams without any restrictions. What's this number? If there are no restrictions of any one person being selected, we still have this condition, remember? We want 4 children, 4 adults and 3 children. So how many adults do we have in total? We've got 7 adults. Out of those 7 adults, we want 4. And then out of the 8 children, we want 3. That's the total number of possible selections where we don't have any restrictions on who is to be selected and who is not to be selected, apart from the number of adults and the number of children. Subtract from this the case number of teams that do not have both Mr. Kenny and Mr. Lizo. If we subtract that number in all the remaining teams, we would have at least one of them, right? So we're subtracting from the total the case where both of them are not selected. Now, in how many ways can we have both of them not selected? The number of children is still the same. There's no condition on children, right? So we have 8 children. Out of them, we have to select 3. Now, if we do not want Mr. Kenny and Mr. Lizo to be selected, if we don't want any of them to be there, remember we had 8 adults in total. No, sorry, we had 7 adults in total. If we do not want Mr. Kenny to be selected and Mr. Lizo to be selected, we only have 5 adults left from which we have to choose now. So out of the remaining 5 adults, we say from those 5 adults, choose 4. So 5C4 into 8C3. That is going to be the number of teams where both Mr. Kenny and Mr. Lizo are not selected. When we subtract this from the total, the remaining teams all would have at least one of the 2 present. Okay, let's see what this turns out to be. 7C4 multiplied by 8C3, and that's giving me 1960 minus 5C4 into 8C3, and that's 280. 1960 minus 280, that's giving me 1680, and that is our final answer. This is one way to do this, or you could make 3 cases where one of them is selected, the other is not selected, and then the other is selected, the first is not selected, and then they're both selected, and then add those 3 cases together. You could also do it like that. Make sense? No problems? No questions?
Sir, can you re-explain it again?
Which particular part of this?
Part D.
Okay, let's try to understand the given condition again, what are they saying? They're saying there are 7 adults in total. We want that at least one of Mr. Kenny and Mr. Lizo must be selected. Now, both of them are adults. So the first thing that we understand from that is there's no condition on children. There are 8 children, we select 3 out of the 8 children. Okay. The condition is on adults. And that condition is that at least one of these 2 people have to be selected. What we're saying is, let's find the total number of possible teams without any restrictions, where we could have both of them selected, not selected, one of them selected, one of them not selected, and so on. That will just be 7C4, select 4 out of 7 adults, and select 3 out of 8 children. That will be the case when you don't have any restrictions. If you subtract from this the case where both of them are not part of the team. So remember that there are 4 possibilities. So Mr. and Mr. Kenny and Mr. Lizo. There are 4 cases. Either both of them are there, or the K is there, L is not there, K is not there, L is there, or both of them are not there. They want the first 3 cases. What we're doing is we're saying, let's find the total that represents all of these cases, 1960. Subtract from that this last case where we're saying both of them are not selected, and that will leave us with these 3 options. Okay, so when both of them are not selected, what that means is we had 7 adults initially, and if both of them do not have to be selected, the choice is now only amongst the remaining 5 people. We had 7 earlier, we removed those 2, and we say out of the other 5 people, we have to select 4. So that's 5C4 and 8C3 for children. And that basically gives you this last case where both Mr. Kenny and Mr. Lizo are not selected. So when we subtract that case from the total, we are left with the first case and the second case and the third case, and that's what we're looking for. Make sense? You could also find these cases directly. Right? You could find the first case, the second case, the third case, and then add them up together. That's also possible. Let me show you that as well if you want. In the first case, let me do it the other way around as well. These are the 3 cases. We could find these 3 cases directly. Remember, we have 8 children. Out of those 8 children, we have to select 3. So 8C3 is going to be in each of these cases. And along with that, we have to select some adults. We have 7 adults in total. Out of them, we have to select 4. Right? Now, the first case is both Kenny and Lizo, they have to be there. If they have to be there, that means from the remaining 5 people, we have to select 2, right? Because those 2 are already selected. So instead of 7C4, we say it's 5C2. And then in the second case, if Mr. Kenny has to be selected and Mr. Lizo does not have to be selected, how many people are we left with? The remaining 5 people. Out of them, how many more do we want? We already have Kenny selected. We want 3 more people, so that's 5C3. And then similarly, in the third case, we're saying Mr. Lizo is already selected. Mr. Kenny is not selected. Out of the remaining 5 people, the other 5 people, we have to select 3 more, right? Because we want total 4 adults. When you have these 3 cases, you find the number of cases, the number of combinations for each one of them, and then add them up together. So this would turn out to be 10 into 8C3. That's giving me 560 for the first case. actually it's going to be 560 for the second as well, 560 for the third as well. You add these three cases together because it could either be the first case or the second or the third, and that gives you 1,680. This could be another way of thinking about this. That gives you the same result as well. Okay?
Okay.
All right.
Sir, please, I wanted to ask, what can I do for mechanics right now? I'm still struggling with answering some questions.
Is it the same for all topics? Are there any specific topics that you're struggling with?
Mostly like the work and energy power.
Okay. So for work energy power, actually you get very similar problems. So there are just 2-3 kinds of problems that keep getting repeated. So make sure that you understand those 2-3 types of problems. So one in which you have to use the work energy principle, work done by driving force that equals change in kinetic energy plus the change in potential energy plus the work done against resistance. You have to use that one principle a lot in those questions. So try to get better at that, how to use that. And then there are some problems where you have power. In the power questions, you often have to do this, that you have to use these two formulas together. Power equals driving force into velocity, and resultant force equals mass into acceleration, the Newton's second law of motion. So keep that in mind as well. That's the other kind of question that mostly comes. And then you have to use some kinematics concepts together with this. Whichever topic you're struggling with. So this is one type of problem, and the other major type of problem that you get is when you have to use this principle, work done by driving force equals change in kinetic energy plus the change in potential energy plus the work done against resistance. And most of the questions are actually solved using one of these two things. Now, if as I was saying, if you're struggling with any particular topics, I would suggest going back and focusing on topical questions on that particular topic. So if you're struggling with work energy power, for instance, or you're struggling with kinematics, do a lot of topical practice on that. Okay, so that you can understand how to deal with each of the different types of problems that you get there. Okay.
Yes,
You have to go through topicals again, do a lot of topical questions, and once you've done like 15-20 questions from both the topics, you will start getting better at it. Make sure that you understand the concepts while you do that. How do we know that we have to use permutations in part B and selection in part C? Well, in part C, it says, in how many ways can the team be chosen? When you're choosing people, the order does not matter. Okay, when you're selecting people, choosing people, the order does not matter. That's combination. In part B, they're talking about order in how many different orders. So that means they're talking about arrangement. So in permutation, order matters. In combination, order does not matter. In permutation, they're trying to arrange people or objects. In combination, just selecting people or objects, and the order does not matter there. So it's clear here. They're asking about the number of different possible orders here. So that's permutation. Here they're asking about how many teams can be chosen. They're both keywords for combinations, where you're selecting people, choosing people, making a team of people. That is combination, because in this case, the order does not matter. Okay. Make sense? All right, so that's it for today then. Tomorrow we will be doing, no, not tomorrow, in our next class, that's going to be on Tuesday, because the next two classes are going to be on M1 now, because M1 is on Tuesday. So before that, so our next S1 class is going to be on Tuesday, and then we'll have daily classes for S1 the next week, inshallah. Tuesday, Wednesday, Thursday, Friday, Saturday. All 5 days next week will be on S1 from Tuesday to Saturday. For Tuesday, you need to attempt March 2022 and November 2022 paper 1 variant 2. And that November 2022 paper 1 variant 2 that also has that famous crocodile question. We will also be doing that in our next class, inshallah. All right, so that's it for today. I'll see you again in the next session. Allah Hafiz.